Thank you for, well, it's nice meeting you all. So this talk is about our recent work on titled Pump Up the Volume, Processing Large Data on GPUs with Fast Interconnects. And it's work conducted together with my colleagues from both TU and DFKI, and of course, Professor Martel. So the goal of our work is to scale GPU-accelerated data management to arbitrary data volumes. And what I mean by this is that if we have several terabytes of data and we want to process them with, say, relational operators, but this could also be ML or other types of operations, then we want to actually use all the hardware resources that we have at our disposal. And nowadays that includes CPUs, but it also includes coprocessors such as GPUs. And these dedicated coprocessors have onboard memory, which is very fast, and it's in the order of gigabytes of data that we can store on there. So it's too small to hold the entire data set. And for this reason, today's GPU databases typically store the bulk of the data in main memory, of which we can actually have several terabytes, and then do an ad hoc transfer of these data to the GPU where we do the processing. And this is a setup that you can find both in academia, such as in the query compiler built by Sebastian Bress, as also in the commercial world, such as in OmnisciDB, for instance. And this ad hoc data transfer occurs over a PCI Express 3 bus nowadays, which has a bandwidth of 12.3 gigabytes per second in both directions. But modern GPUs are capable of processing data at a much higher rate than we can actually achieve with this particular interconnect. And thus the interconnect bandwidth combined with the GPU memory capacity limit the scalability in terms of data volume that we can actually process on these GPUs efficiently. And this is a very well-known problem in academic literature called the transfer bottleneck. There's a second problem that's related, and this is that these databases are often constructed in such a way that they transfer these data in chunks. And the CPU decides which chunks are transferred in which order. And for this reason, the GPU cannot perform data-dependent memory accesses to data residing in main memory. It can only perform these types of accesses to GPU memory. And furthermore, these chunks are several megabytes in size, so they're actually quite coarse-grained, and thus fine-grained coordination and cooperation between the CPU and GPU is not really possible. And the thing is, we need both of these properties to construct mutable data structures that we share between these two types of processors. Thus, the non-cache coherence property of this PCI Express interconnect limits us in the design space of how we actually build databases and how we do co-processing between the CPU and the GPU. For these reasons, we propose to investigate and use fast interconnects in databases. And fast interconnects are a new class of technology that's coming out now from 3 different vendors. So the first is NVIDIA with NVLink 2. This is already out, and this is what we've measured. Then there's also AMD with Infinity Fabric and Intel with Compute Express Link. And I'll get into these a bit later in the talk. What these interconnects have in common is that they offer high bandwidth and system-wide cache coherence. And in the case of NVLink 2, the bandwidth is, in theory, up to 124 gigabytes per second. And we can actually get quite close to that in actual measurements. So on the right, we're seeing 120 gigabytes per second, which is 6 times faster than what we have with PCI Express 3 for a bidirectional transfer. And the system-wide cache coherence property is also important because this allows us to do these types of data-dependent memory accesses from the GPU to main memory. and also do more fine-grained CPU-GPU cooperation. So the contributions that we make in this work are that we perform an analysis of the hardware, that we measure different data transfer strategies to find the one with the best performance for databases. Then we investigate a concrete operator, in our case, a join. And we also investigate a cooperative co-processing approach for CPUs and GPUs. And since I was told we have some time in this talk, it will be interesting to see a bit more. I've extended this talk to show the hardware analysis and also present here some work which is not in the paper. Then we're going to take a look at the join operator. We're going to look at the co-processing approach. And in addition, we're also going to look at the hardware availability of these types of interconnects. And if we have some time at the end, where I'd like to show you a bit of a demo about how to actually use these types of interconnects. So let's start with the hardware analysis. And first off, let's take a look at the bandwidth. So here I'm comparing the bandwidth of NVLink 2 for unidirectional transfer with CPU memory, with NUMA interconnects between CPUs and with GPU memory. And essentially what we're seeing here is that NVLink actually for unidirectional transfers doesn't quite reach the bandwidth that we have on this particular Power 9 machine for a single socket. But it's also not that slow anymore. So we are within a factor of 2 of the main memory bandwidth. And if we actually compare this to a fast Intel Xeon CPU, a recent one, we can see that we're actually approaching where the Xeon is. Whereas if we look at the NUMA interconnects, we can see that the NVLink bandwidth is actually much higher than the UPI interconnect between 2 Xeon processors and the XBus between 2 Power 9 CPUs. But still, if we look at GPU memory, I mean, it's clear that GPU memory is still an order of magnitude faster than the interconnect. So there's still a big performance difference there. So the key takeaway here is that GPUs do have high bandwidth access to CPU memory now. Looking at the latency, this is actually a plot which I did not include in the paper because it's a bit more detailed than I was able to fit. So what we're measuring is pointer chasing, where we have the range in kilobytes on the x-axis and the latency in nanoseconds on the y-axis. And I'm comparing the GPU memory and the CPU memory as accessed via NVLink from the GPU. And what we can see is the different cache levels. So we have the L1 cache of the GPU. We have the L2 cache of the GPU for GPU memory, but this is actually missing for CPU memory because it's on the side of the GPU memory rather than on the side of the streaming multiprocessors. So we bypass it when accessing CPU memory. And then finally, we hit memory, and we see that the latency of CPU memory is 54% higher than for GPU memory. So the takeaway here is that GPUs have relatively low access to CPU memory. I mean, this is relative to GPU memory. Since GPUs are actually built to cope with high latency accesses, this isn't so much of a big deal. But what's also important for us when we architect databases is the cache hierarchy. And it's important to note that the GPU cache hierarchy is different for CPU memory than it is for GPU memory. Coming to the join operator, what we're doing is we're constructing a hash join operator, and we're keeping this very simple. So we're basically assuming that we have perfect hashing just to be able to actually understand what's going on the device. And we're investigating 3 different things. The first is the probe size scaling. The second is the build size scaling, and finally the CPU GPU cooperation. And for the probe size scaling measurement, the setup is as follows. We are storing the bulk of the memory in, or so the base relations in main memory, and we're performing ad hoc transfer of all the data to the GPU. So we're not assuming any caching or anything like that. And on the GPU, we're performing the join by first building a hash table in GPU memory and then doing lookups in it. And the key feature that we're investigating is the high bandwidth of the interconnect. So in the measurement, we're scaling the probe size, so the probe relation size, up to 122 gigabytes. And we're keeping the build side relation constant at 2 gigabytes. And we're measuring on the y-axis throughput in gigatuples per second. And I want to point out that this size of the data is much larger than GPU memory. We're measuring 3 different strategies. The first is a CPU join using a partitioned radix join on a recent CPU. Then we're measuring a GPU join. This is a no partitioning join with PCI Express 3. And on the same GPU, we're also doing the measurement with NVLink 2. And what we can see is that moving from PCI Express 3 to NVLink gives us a 6x speed up. And it's actually even a little bit higher in our measurement here than the CPU baseline that we have. So the takeaway is that GPUs can now efficiently process large out-of-core data sets. For the build side scaling experiment, we changed the setup a bit. So instead of building the hash table in GPU memory, we build a hash table in main memory because this allows us to scale the size of the build set relation to something that's bigger than GPU memory. But otherwise, we're keeping the exact same setup. And the key feature that we're investigating is the data-dependent memory accesses to main memory from the GPU. And in the measurement, the experiment is very similar. The difference is that we're scaling both the build side and the probe side relation sizes up to 30 gigabytes each. And that will give us a 30 gigabyte hash table. So the total size that we're storing in main memory is 90 gigabytes. And here, the size of the hash table that we're constructing is much bigger than GPU memory. So what we see in the measurement is for NVLink, if we move the hash table from GPU memory to CPU memory entirely, then we're reducing the performance by 85%. And of course, we see a similar drop in performance for PCI Express 3. However, even though that number of this 85% drop in performance is quite large, we're 18 times faster than the same thing with PCI Express 3. So just moving from PCI Express 3 to NVLink gives us a huge boost in performance. Also notice that we're roughly on par with what the CPU achieves here with NVLink. So that's actually also quite good. But even though it's much better than what we had previously, it's still not quite optimal. So we came up with a new strategy called a hybrid hash table. And what we're doing is we're spilling only those parts of the hash table that don't fit into GPU memory to CPU memory. And so we're actually caching as much as we can in GPU memory. And what this gives us is a bit of a smoother curve. So we, of course, still have a decline and eventually reach the same performance as without this strategy, but it smooths the curve a bit. So the takeaway here is that GPUs are able to operate on large out-of-core data structures now, thanks to NVLink. And the second takeaway is that we should still try to cache data structures in GPU memory as far as we can, simply because GPU memory has so much higher performance than the interconnect does. Coming to the cooperative co-processing, we're again building a similar experiment. The difference is that before we were only using the GPU, and now we're adding the CPU to the mix. So we're doing both the build and probe on the GPU simultaneously on a mutable shared data structure together with the GPU. And so the key feature of the interconnect that we're investigating is the cache coherence property that allows us to do this. So we have 3 different workloads that we're investigating. The first is a workload where we have a 16 times difference between the inner relation and the outer relation, where the inner relation is 2 gigabytes and the outer relation is 32 gigs. The second workload is targeted such that the inner relation fits into the caches of the 2 processors. So it's quite a small relation of just 4 megabytes. And the third workload has 2 relations of equal size. And we're investigating 4 different strategies. The first is a CPU strategy, this time on a Power 9 CPU and using the same algorithm that we're using on the GPU, so a no partition hash join. And the second strategy is a heterogeneous strategy where we're extending this CPU baseline to work together with the CPU. So here the hash table is in main memory, and both CPU and GPU are simultaneously building and probing on this hash table. And then we have a third strategy, which is an optimization for small inner relations. So this is a GPU plus heterogeneous strategy where we're first building the hash table in GPU memory using only the GPU, and then we're giving the CPU a private copy of the hash table to work with. So there's actually 2 hash tables at this point. And finally, we're investigating a GPU baseline where we have only the GPU with the hash table in GPU memory. So we have 2 takeaways from this experiment. The first is that scale up using coprocessors works. It makes performance more robust, giving us higher performance in some cases, but it doesn't give us higher performance in all cases, particularly on the very right. But still, we're avoiding the worst case of a strong performance degradation. And yeah, I mean, what we can also see is that the GPU-only strategy can be significantly faster in some cases than a heterogeneous strategy. So I'd like to also speak a bit about the availability of these types of interconnects that make this work possible. And so the type of interconnect that we're using here is NVLink 2. And this is concretely in an IBM AC922 machine with 2 Power 9 processors, 2 GPUs, even though we've only used 1 for our measurements. And yeah, since there's no information on the IBM website about the cost of this machine, I'm just going to pitch that this is roughly $40,000 for academic pricing. And I also found that we can rent these machines by the cloud vendor Cyruscale. So the smaller cloud vendor, but they offer these machines for $3.30 an hour. So this price was taken beginning of this month. Yeah, so there is availability for this hardware right now. And of course, it's also being used in some supercomputers like the Coral supercomputer. Now for Infinity Fabric, the story is different. This exists right now, currently. It's available for purchase, but only if you're actually purchasing a supercomputer. So like this type of, it's called a Cray Shasta. And I mean, it costs obscene amounts of money. But it actually has this interconnect between the CPU and the GPU, in addition to between the CPU, the GPUs, like you can actually purchase by yourself right now for the AMD GPUs. And yeah, this is being used in two supercomputers, Frontier and El Capitan. The story is a bit similar for Intel with their Compute Express Link. They're saying that it will be available for purchase in 2021. And they've announced this for their CPUs, GPUs, FPGAs, and even their RDMA network cards. So everything that Intel is building is supposed to be able to use Computer Express Link eventually. And they also held a keynote at Damon 2020, where they were advocating this a bit. But yeah, it's so far it's not available yet. And I guess at this point, I also need to point out, why am I including Intel in the list of GPU vendors? Right now, they're only selling integrated GPUs along with their CPUs, but they've also announced a Ponte Vecchio dedicated GPU architecture that they also plan to release in 2021. So yeah, they will become a GPU vendor according to their roadmap. Yeah, so this brings us to the conclusion. What I'd like you to take home from this talk is the ways in which fast interconnects can benefit databases specifically. And there's 3 points. The first is that we can scale the volume and size of data sets. We can scale to large data structures, and we can investigate and do different new things in the cooperative co-processing between CPUs and GPUs. So with that, I'm done with these slides. I'd move on to the demo, but I suggest we do a Q&A first before we come to the demo, so we have sufficient time for that. And yeah, I'm happy to answer your questions.
Thank you very much.
And please speak up for your questions, because I actually don't see when you raise your hand with Zoom on my screen.
So thank you very much. Maybe I can start.
Yes, go ahead, Mark.
Very interesting work. Thank you for the presentation. So we have actually done a paper on GPU code processing. So it was quite related. We were doing query one, TPCH query one on GPU and CPU. But we found that the main bottleneck for the GPU was the transfer, which of course this NVLink stuff does a good job of mitigating. One thing that we thought was interesting is usually people kind of have the choice, or they are building a machine or a server. And when you talk about this co-processing, the question is mostly, what am I going to buy? Am I going to buy another CPU, or am I going to buy another GPU? Mm-hmm. Do you think that, given that your performance numbers, that it makes sense to say like, okay, I'm going to buy a server, should I stick a GPU in it? From like a monetary perspective, do you think that makes sense now? Or do you still think that the CPU is just more general, let's say?
Okay. So before I answer the question, I have a question back quickly. Are you, the work that you've talked about just now, is that the Bloom filter approach for the joins?
No. It's a
different one.
It's ADMS. It's query one. I think I have to remember the title.
From 2 years ago.
Okay.
Yeah, it's 2 years ago. I kind of forgot the title.
It's optimizing group buying aggregation, CPU, GPU co-processing.
Yeah, that one.
Okay. Yeah, that's a completely valid point. So I would say up until now, there's been a very limited set of use cases for databases where GPUs would make sense. And that's in particular what works all the way back to the first Bing-Xing He papers, for instance, pointed out, is that GPUs are very good at performing joins and group aggregations as long as you're in GPU memory. So as if the data structure fits into GPU memory, you have a good chance of being faster than if you move to CPU memory. Now with CPUs becoming faster and the interconnects with PCI Express 3 especially haven't been keeping pace for a long time, simply because there was no evolution in the interconnect space. And that is now changing. So I think that, yeah, these machines within VLink 2 are still a bit of an exotic beast, in that they're not x86 processors, that they're very expensive compared to x86 machines. So yeah, in that sense, I would say it's probably a hard choice to take at this moment if you're going to build a machine. But I mean, there's also machine learning out there that's where you actually have machines dedicated to that type of workload, and if you can run a database next to it, that might also be a worthwhile investigation.
That's a good point. If you already have a GPU anyway, then it's just the value proposition changes, let's say.
And also, I mean, this is a bit looking into the future of there is finally activity going on in the interconnect space where it was not previously for many years. So this is essentially what we're trying to point out, that there's new opportunities opening up, and we should keep an eye on them and investigate what uses GPUs now can have for databases.
Oh, for sure,
So
I agree.
this,
Very interesting stuff.
so
So another work out of our group, a small one by Holger Pirk a couple of years back, also looked into GPU CPU co-processing, and back then we concluded that adding a 500 euro or dollars GPU to a 50,000 whatever dollar server can double your database performance. So it's always a question of how to put that. Back then it was still
yes.
in the very limited PCI Express times, and Holger had this idea of putting low resolution data, if you read, on the GPU, not for joint processing that much back then, mostly for filtering. But it worked quite nicely, so that adds to the whole picture as well. But this is also very interesting work. I have lots of detailed questions, but let me get to a more general question and start from the very end, namely an outlook. So, as you said, this is just about to happen. Well, it's technically happening, but not yet market penetrating, if I allowed to say so. And let's put it like this: hardware vendors, probably not for us, but for others. And hardware vendors never listen to database people. We simply don't have the market. But because others, among others, the machine learning people you mentioned, and gaming, and who knows what, need this, or they had an idea how to do this. They make our life easy, seemingly. It's just like now we have a co-processor and we have high bandwidth, and we can play tricks where it all falls into our advantage, and we don't need to do a lot other than thinking, which parts do we put there, and do we kind of let them integrate or collaborate or not. And in fact, as you showed, the latter picture is not that easy to decide, and using it can be beneficial. Do you see any core challenges where we as database people have to say, like, yeah, we have bandwidth, and we already know how to use GPUs for database algorithms and things like this. What is the key? What do you expect being the big challenge to make this, to use these efficiently, other than the things you presented?
Yes, you're absolutely right. There are very new challenges that are emerging now with these interconnects, because bandwidth isn't everything. I mean, the key things that I'm considering are that on the one hand, we still need to optimize for processing data out of core, in the sense that we do want to use GPU memory, because this is the main advantage for databases, in my view, of GPUs, that we have a fast cache. So we need to optimize our data processing to actually use this cache. And of course, some of this has been going on, but now the trade-offs have shifted a bit. So there's also new opportunities, I think, that we can explore there. And the second point that I've been thinking also a bit about is that yes, we have cache coherence, but if we take a closer look here at what happens here on the right chart, for instance, take a look at the CPU and the heterogeneous bars. They're very close together, even though we're using two devices. So yeah, we can have a mutable data structure where both processors are operating on it, but this clearly needs optimization. So if we have a setup like this and we want to use it, we need to think very closely about what is the performance of not just the bus, but also of the protocol that's going over that bus. Because what I found is that the cache coherence protocol that we're using for NVLink is something much more simple than what we're used to in CPUs. So specifically, in CPUs, we're used to that if two cores access the same cache line read only, then both of them can have a copy in their L1 cache, for instance, right? So this is a state in the state machine, but it's not the state in the state machine that NVLink currently uses. So it's either you have access exclusively or you don't have access at all to a particular cache line. And these kind of things also present challenges for us as database people when we're thinking about how do we do the co-processing.
So it's not something like shared usage and invalidation. It's more like stealing it.
Yeah. And it's actually, it gets more complicated than that. I'm not sure if I want to, how much I want to go into this right now in the talk, but I'm happy to send you some links as well. So essentially the core constraint for designing this interconnect was that you have two big corporations that are cooperating together, and they don't want to change the design of their respective processors very much. Mm-hmm. So they needed to, so this was actually the first design goal, not performance, but trying to limit the changes to the processors. Mm-hmm. So the protocol that's and the whole design of the bus is really laid out in such a way that the cache coherence protocol is a bit of an add-on to the link that's going on underneath.
Yeah, but
yeah,
you know, with nowadays tendencies to take any kind of collaboration, even on this multi-core CPU thing in particular in NUMA settings, but also simply for definitely cache coherence across shared caches, mm-hmm. Beyond shared caches, going like treated as a distributed system. I think the heterogeneous here is a nice thing to have, but I wasn't really expecting it. I didn't know that that's the main bottleneck, but I didn't expect to work much farther. The GPU plus heterogeneous is an interesting fact, and the graphs nicely show where the benefits and limits are. So something in these lines, I suppose, yes, let them cooperate, but make sure that they cooperate in, very coarse grain. Despite that fine grain seems to be on paper technically possible, it doesn't perform as you just detailed.
Well, it's yeah. At least not in this case. I mean, this is also something that throughout the paper I was following, and including in this graph, I'm always showing the worst possible case for the interconnect and for the GPU. Mm-hmm. So of course, if we would say, for instance, that the hash table does not fit into GPU memory, then the story becomes a bit different here in this particular graph, for instance, because we could not perform the GPU plus heterogeneous optimization. So that's just out of the picture.
If you desire to build a single shared hash table.
Yes, absolutely.
there are other ways to do it. Actually, I must confess I was a bit interrupted due to a phone call at two earlier stages in your presentation. Two phone calls, so I didn't get all the. But you also mentioned partitioned hash joins, right? You do partitioned hash joins on the CPU only.
Yeah, this is again along the same line of argumentation. We wanted the best performing CPU join that I could find, which was a partitioned hash join by the ETH guys. So this was Charlie Barkesen's work, and I measured this on the fastest CPU that I had at my disposal here in our group. So this is a 12-core Intel Skylake SP CPU. And yeah, this is the performance that I get for that hash join. I mean, I'm sure that there are cases where a no partitioning hash join could, I mean, there are cases, we all know that the no partitioning hash join on the CPU can also achieve good performance in some limited cases. But since I was actually scaling to big sizes, I decided to go with the radix join. Again, if we can, of course, also do a radix join on the GPU and get different performance. But yeah, my line of argumentation is here really what are the limitations to be able, of the interconnect, to be able to understand these and to present them versus in the well, most suboptimal light possible, to show that even in this case, we actually get the big speed up.
Okay. Is these numbers, are they only showing the probe phase timings throughput, or is this the general
This is
throughput including the build phase?
This is both. This is the entire join.
Okay. That's interesting. But then your build table is relatively small compared to the probe, so that
yeah.
Well, at least on the right side. That's okay. That explains.
Yeah, here here the build table is growing, and then we see a bit of a decrease in performance. And I mean, the GPU at this point is just limited by other factors. So for the PCI Express bus, well, it's limited just by the data transfer of the base relations. And for NVLink, it's actually, it's a bit of a close gap, as you can see here as well. But the actual limit is not the interconnect, it's the random accesses to GPU memory. Although it's a close call, to be honest.
Yeah, okay. So, I was actually wondering with this one, if you use NVLink and your build table or your entire data size, in particular build table, goes out of GPU memory, you're so nicely hitting the theoretical or no practical PCI Express throughput line. Why you're not? Are you actually using? Oh, you're still using it. You're still running it on GPU, but with the data in CPU memory, right?
Yes.
Okay, so actually you are bound by the PCI Express.
Yes, and I mean, essentially why, I mean, I'm showing that the performance gap here actually grows for between PCI Express and NVLink from about 6 times to 18 times. And this, I think this is a factor of latency then in the end, and how good the buses can handle small random accesses. And so, yeah, with NVLink, it's just simply much better than with PCI Express 3. But this, I think there's also some backstory to this, because initially I was not using perfect hashing, but rather I was using linear probing. And for linear probing, you have at least two accesses. So in the best case, without conflicts, we had 2 accesses in our implementation per lookup or insertion. And of course, that paints again a very different picture than the no perfect hashing. So yeah, but this is something I didn't really want to get into in the paper, because there's so many different strategies that you can apply. that I didn't want to distract from the main story.
Yeah, there's room for more work.
Yes, definitely. There's
So
lots of room.
final back to this one, I just misread the figure. So here actually your blue and your brown line meet. So GPU processing using NVLink versus CPU processing. Why do you want out of core merge build tables get exactly to CPU only performance when using GPU with NVLink?
Okay, so one of the things that you need to note here is I don't actually have the Power 9 CPU in this graph, simply because the implementation by ETH was optimized for x86. And so I thought I would want to present them in the best light I can, and not do my own port at this time to Power 9. So I would claim if you were to run the same algorithm tuned for Power 9, you get a bit better than that, actually. So
okay, but the numbers are the x86 code run on the Power 9, so to speak.
No. It's x86 code run on x86.
Okay.
But the NVLink is on a Power 9 machine.
The NVLink is on Power 9. So the fact that they get the same performance is more like coincidence.
Yes, it's absolutely coincidence.
That's striking. Okay. Okay, I see. Thanks.
So,
anybody else?
I do have a question. Hi, Clemens.
hi.
I was wondering about the division of work when you have the co-processing experiments, because we had this paper, you mentioned the Bloom filter paper last year at Damon, and
yes.
there we found out that there is no good balance between GPU and CPU if you want to have this co-processing thing. I mean, it's not equally balanced. So we had to give basically more tuples to the GPU to minimize the data transfer. And I was wondering if this was the case for you as well, and if you found out something different.
Yes, you're absolutely right. We had the very same issue. So we're actually using I read your paper. I quite liked it, actually, and we're using a very similar approach to what you presented. So also with a morsel-driven parallelism between, so for the yellow line here, the heterogeneous especially, but I mean also for the GP plus heterogeneous. And yeah, so we saw exactly what you're saying. The GPU will get starved by the CPU if you just simply let it run. And I mean, at this point, my assumption is, since I've seen this before in my previous work for K-means on PCI Express, my assumption is that CPU, the memory controller, is designed in such a way that it gives priority to accesses coming from the CPU rather than from the I/O controller. So to balance that, what I did in the previous paper was I artificially slowed down the GPU, the CPU, so that it would fetch less and perform some additional work. I didn't do that here. I didn't want to. What I did instead was I increased the morsel size of the GPU to something much larger. So we're actually using, I think, 1 gigabyte morsels here for
quite large.
Yeah, for quite large for the GPU. I also need to add that the implementation is not optimal for our morsel-driven strategy. So because we don't have overlap between. So essentially, the GPU kernel terminates, gets a new morsel, and then restarts. And there's some small gaps there where it's not doing anything. So you could probably increase performance a little bit more simply by launching an asynchronous kernel as well. So yeah, there's surely more performance tuning that you can do, but yeah, generally this story is exactly what you say.
Oh, very good. Thanks for the answer. And very good paper. Congratulations.
So would you like to move on to the demo, or would you like to ask some more questions?
Unless somebody shouts a question right now, yes, please go on with the demo.
Okay. So, right. So what we have in the demo, what I'm showing is how do we actually program one of these GPUs that has a fast interconnect? Because I know some of you have some experience in programming GPUs, but even so, this is slightly different. And what I'm going to show is three different strategies. The first is the coherent strategy, and the second is the zero copy, and the unified migration. So zero copy is also called unified virtual addressing, and unified migration is essentially just unified memory without any additional tuning. And before we go on to the machines, I want to show you what is the topology of this machine. And so LS topo on this particular Power 9 machine shows us that the GPUs are visible to the operating system as NUMA nodes. So this is something that's new compared to previous interconnects. Yeah, so let's dive into the demo, and the code is also available online for reference. I can come back to this slide again. So I'm logged into two machines. The one is an NVLink machine. The other is a machine with, this is an x86 machine with the same GPU, just connected with PCI Express 3. And oops, what I want to show you is if I go here and I open some code, this is what we're doing here is we're just taking a vector and adding a constant to all of the elements of the vector, right? And this is CPU code at the moment. And I'm going to step you through how we transform this piece of code into GPU code using a fast interconnect. And after that, I'm going to contrast this in how we would do this. I'm not going to write everything, but just open the other files, and how contrast this and how we would do this for a PCI Express machine, and what is the difference and the benefits and drawbacks. So just to run you through the code, we have a vector of length 100,000, so something a bit bigger. We're just going to allocate the vector in main memory with just simply malloc here, nothing special. And yeah, init some data, and then call this function. And after that, we're going to check. We're going to after running the function, we're going to again access this vector from the CPU. So I'm just basically checking that the code is correct, but the relevant part is that we're really using the CPU to run over this vector again. And so when we transform this to GPU code, we don't need to change much. All we need to do is the usual, add a global bit there, and just make this a coalesced parallel stride, the access to the vector. So I'll just calculate what is the grid dim.x times the block dim.x, and unsigned g index equals the block dim.x times the block index.x plus the thread index.x. And then we're just going to modify the loop a bit with this, and g size, sorry, I plus equals g size. So that's it. We don't need to perform any more modifications to make this a GPU kernel. Now it's a parallel access with the coalesced memory access pattern. And then I'm just gonna specify the grid dimension to something that's good for this GPU, as well as the block dimension. And then we're almost done because we just need to pass this in. Grid, block, that's it. And now, so wait, I compiled this before, so I'm gonna just show you before I recompile that the CPU code was working. So it gives us a 0 exit status saying that this ran through, there was no assertion triggered. We had no illegal memory accesses on the CPU or anything. So let's go ahead and recompile this with my changes. Okay, so I somewhere made a mistake. Okay, that didn't go to plan. I actually practiced this beforehand, but somewhere I must have made a small mistake. So let me just recover this and show you. So instead of finding it now, let me just open the same thing. So this is exactly the same thing. It's just pre-written. So again, the block size, grid size, everything is, whoops, everything is the same. So let's just compile this. This is the right. So this runs through, and yeah, now we're running this code in parallel on the GPU. And again, note that we've not changed much. So, okay, in this code, we're using a NUMA allocator on the CPU to allocate on the CPU's NUMA node. We could have also used malloc. So that's what I wanted to show, actually, that we don't need to change the allocation. And we, after running on the GPU, we just wait for it to complete, and then we access the array on the CPU directly. I mean, in this case, it's actually even residing in CPU memory. So I'm just trying to show how easy it is to move from CPU code to GPU code. And in databases, well, we're used to working with bigger machines that have multiple sockets and using NUMA accesses and optimizing for NUMA in our databases. So if we have code like that already, it becomes even easier because just to move from main memory to GPU memory, all that we need to do is change the node here. So we're just going to change the NUMA node from 0 to 255. I'm going to recompile this, run it. It returns the same results. We did the same operations on the CPU and the GPU, except now we're actually using GPU memory. And we're accessing GPU memory from the CPU directly in the verification here. So this is something that you cannot do just simply like that with if you're allocating device memory. So integrating this into existing code for CPUs is not so difficult. Now, if we now move to the other machine, I can show you just the CC GPU demo. So this is the same code. This is actually the malloc code for some reason, but which file was this? This is CPU. Okay. So let's go ahead and compile this again. This was demo. think I need to link in Numa. There we go. And this crashes because the GPU code, actually it also has an invalid memory access, but we're not even coming to that point. What we see before that is that in the verification loop, nothing changed because the GPU never touched this array. So we're getting an assertion because the results are wrong. So this trick that we played on NVLink, it does not work on PCI Express. Now,
short question.
mm-hmm.
So here we see the same problem as you tried to show before with the NVLink, where you have two files, and once you edit, it still had the malloc, and the ones you resorted to had the NUMA malloc. So
yeah.
Was the initial idea that the simple malloc works with NVLink?
Yes. Yeah. This is what the original idea behind.
Sorry for being picky on this, but I just try to understand what was.
Yeah, I'm sorry about that. I must have mistyped here somewhere on the NVLink machine. So I was actually trying to show initially that the CPU, so that this code works with malloc.
I understand, but I don't see.
I'm sorry. I know what's wrong. CUDA device. Yes.
Good point, yes.
There you go. Now it works. So this is simply using the normal malloc, and this is exactly the same code that we had on the other machine.
Wait.
So was that the question?
Yeah, that was the question.
Okay.
You know, triggered, I wouldn't have bothered you, but triggered by the fact that exactly your showcase failed the same way on PCI Express, and that's how you show that the malloc version doesn't work on PCI Express.
Yes.
Triggered me to say, like, well, show this. No, thanks. Sorry for you, but thanks for.
No, you're absolutely correct. Thank you for making this point. And yeah, I'm glad that we just found the mistake. So how would you do this with PCI Express? What we would typically do is, I have this here in the CUDA demo. So this is the same kernel, essentially the same code. What we're changing is how we allocate memory. And of course, there's the three different ways of doing this. So the most basic way is we allocate device memory on the GPU, and then we can actually run on these types of kernels on the GPU. The thing is, this doesn't actually work on neither NVLink nor on PCI Express, because the CPU does not have access to this CUDA malloc device memory. On PCI Express, it's physically not possible in this way. On NVLink, the reason is a different one. It's because the pages are not mapped on the CPU. So the CPU cannot actually access the pages, even though the interconnect would support it. So that would definitely lead us to a segmentation fault on one of the two devices. Then the other way is by allocating pinned memory. So this is also called unified virtual addressing or zero copy. This works on both devices, so both on the GPU, on NVLink as well as on PCI Express. On NVLink, it doesn't give us any benefit at all. On PCI Express, well, the benefit is that we can now access CPU memory at the cost of pinning it. And in the paper, I have some links to why you would not want to do this, because it effectively costs to allocate and manage this type of memory. And the third way is with unified memory. So this is an abstraction by the operating system where now this code as it is would actually work just like it does on NVLink. The difference is that we have some overhead going on in the background where the operating system is paging memory in and out of the GPU depending on which device is accessing that page. So yeah, I mean, if you like, I can run them, but I can tell you it's going to work. So I actually already compiled these. I think no, I didn't. So minus three. I don't need to. What? Do I not have this? Ah, sorry, CUDA demo. Yeah, so the CUDA demo on the PCI Express, we didn't change this code, so it's still accessing something that's illegal. What are we accessing here? This is the CUDA host alloc. So this is pinned memory. Now why is it? Maybe I didn't recompile. Okay, we should actually be seeing a result, but it also didn't crash. Status, not result. Yeah, so with pinned memory, this works. It also will work with managed memory. Can recompile and run it again. And it does not work with CUDA malloc. And I mean, yeah, this doesn't work because the CPU cannot access the device memory, even for the initialization of the vector. So yeah, I would say the takeaway here is that yes, we can, of course, use and have cooperation between the CPU and the GPU, but we need to do more modifications to existing code bases because we need to integrate these special memory allocations into our code rather than just simply using whatever the operating system provides us with that we're already using most likely in some way or other. Then, yeah, do you have any questions at this point? So please just go ahead and interrupt me if there are questions.
Yeah, actually, I would have just a clarification that might have gotten a bit lost. So apologies if I'm not following it well enough. So this was all about like how can we access host CPU memory from both CPU and GPU, right? Or that's at least that's what you do on NVM on NVLink.
Yes, and also we can do the other way around. So when we're in, where is it?
NVLink also provides quote transparent access from the CPU to GPU memory.
Yes, this is what we were showing here. So we just changed the NUMA node.
Yes, of course. Yes, yeah, sure. Hey, great. Okay, thanks. What's the granularity? This is the cache line, and what's
the granularity is on cache line? Yes.
Cache line. So it's something like 64 byte.
That's 128 on NVLink. On Power 9.
Yeah, okay.
Yeah. Yeah, and I mean, this allows us to do other interesting things as well. So if we don't want to use C and C++, what we can also do is, I've actually been using Rust quite extensively. So essentially what we're doing, what I'm doing there is I have a small CUDA CUDA file where I just have the kernel for the GPU. And the important thing here is that we need to regard the symbols when we're exporting this to other languages, because CUDA is C++. So here I'm saying, okay, use C symbols, please. And we can then, for instance, use a library in Rust that wraps the CUDA calls natively, so that it's a very lightweight wrapper called Rustacuda, written by someone else. So I've just been using it and inspecting the code, and then we can actually launch this CUDA kernel from Rust. And apart from that, this is the same logic that we had previously in C++. Yeah, then that also allows us to just use all the Rust infrastructure with cargo to build and run this code. So it's building and it ran, and the status is again 0. So we cannot just use CUDA with C++, but NVLink actually makes this very easy to also use other languages. In this case, Rust. But if you want to use Go or Python or anything else, it also has benefits. So yeah, that's the end of the demo. The code for everything that I showed you is online on my GitHub. Feel free to access that, modify it, use it however you like. And of course, also feel free to ask questions via, if you have follow-up questions that you haven't thought of right now, feel free to write me a mail. So.
Okay, from my side, thank you very much, Clemens. It was a very nice talk, very interesting work, and also very helpful and inspiring demo. Virtually, if we had the hardware, we could instantly start hacking. Sometimes these very simple things help a lot to lower the threshold of getting started. Unfortunately, well, we do have a Power 9 purchased. It's physically here. It's, as far as I know, not yet accessible, and I'm not sure what configuration is other than the Power 9. I don't know whether they all have NVLink support, and if so, what kind of GPU is plugged into it. But we will clarify this soon, I hope.
Okay.
Any more questions?
None from my side. Thank you very much, Clemens. Very nice talk.
Yeah, thank you very much, Clemens. Very good talk indeed. Okay, then I guess also in the interest of time and weather here in Amsterdam at least. Sorry, Clemens. Yeah, again, thank you very much. I guess if there are any questions or so, people will contact you. And yes. Otherwise, greetings to Berlin. Some of the people might know some of us. And well, good luck and success with finishing your PhD. I'm pretty sure it will be successful.
Thank you, and thank you for the invitation.
You're more than welcome.
That means see you around.
Thank you. Okay. Bye-bye. See you guys.
Thank you. Bye-bye.
Bye, everyone.